Here I will explain. Determine the magnetic potential at a distance point due to a small circular loop of radius rho carrying a current of I amperes. Carrying a current of I amperes. Consider a circular loop. Use a cylindrical coordinate system. Use cylindrical coordinate system here. This one is x, y, x, y, z. One is consider a small this one is circle. This one is circle. Radius of that circle is rho. This one is phi. We use a cylindrical coordinate system. In this, consider a small current element. This is the small current element length is dl. Length is dl. Find out a dh at a point P here. This one is point P. This one is point P here. R vector R. This point P is on the axis of the circular loop. This one is Z. This one is Z. And one more important point here is this circular loop carries a current of I amperes. Carries a current of I amperes. Find out the magnetic potential at a point P. Important points here. This is the circle. Let us consider a circular loop having radius rho. Carrying a current of I amperes. This is the circular loop having a radius rho carrying a current of I amperes. Let us take a point P. This is the P on the axis of the loop. Z-axis is the axis of the loop at a distance Z from the center of the loop. The center of the loop is 0. Now find the magnetic field at a point P due to a small current element of length dl. This is the small current element of length dl here. Consider a small current element of length dl on this circular loop in xy plane. This is the small current element of length dl. Let r be the r bar is the vector. R be the distance between this current element dl and point P shown in figure. Important point here is first one is let us consider yes circular loop having radius rho carrying a current of I amperes. This is the current is I amperes. Circular loop is indicated in green color. Second point is let us take a point P on the axis of the loop. This is the P is the point take on the axis of the loop. The loop is that is the Z axis at a distance at a distance at a distance Z at a distance Z from the center of the loop. Center of the loop. Now find out the magnetic field at a point P due to a small current element of length dl. Now find out the magnetic field intensity at a point P due to a small current element of length dl shown in figure. Let r be the distance between the current element and point P. And another important point is let r bar is the distance between the current element and the point P shown in above figure. This is the description of the small circular loop having radius R carrying a current of I amperes shown in figure. Here we use cylindrical coordinate system. Here d phi, a phi, here a phi unit vectors. This one is a z. This one is a rho. Now I will concentrate on find out dl and r vector by using cylindrical coordinate system. In case of a cylindrical coordinate system, differential length dl is equal to, we know that dr ar bar plus r d phi a phi in cylindrical coordinate system means d rho, not dr. Here we use a d rho. We use cylindrical coordinate system. dl is equal to d rho a rho plus rho d phi a phi bar plus dz bar. dl here dl is tangential at a point 1 here in a phi direction. dl is the tangential at a point 1 in a phi direction. This one is a direction. Therefore, D row A row is 0. D row A row bar is 0 because the current element is along an A5 direction only, not AZ and not A row, because it is a tangential to that at a point 1 circular loop. Therefore, DL is equal to DL bar, DL vector notation, rho D5 A5 bar only. Now let us calculate, find out R vector. Here consider this one, 3 coordinate system, X, Y, X, Y, Z. This one is a circular loop, point P here. This one is rho, phi, small length, current element of length DL. This one is P here. Here A phi, A Z, and A R, A R. A rho, not R, A rho. In this direction, A phi, DZ, arrow. Here arrow outward, for inward it is minus arrow, minus arrow. Here AZ, AZ. Therefore, vector by using vector addition, R dash is equal to minus rho arrow plus Z into AZ. This is the vector R bar. According to Beveridge-Savart's law, according to Beveridge-Savart's law, the formula, the magnetic field intensity at a point P is, due to that small current element is DL, is DH is equal to I DL bar into cross R cap by 4 pi mod R whole cube, mod R whole cube. That R is equal to R bar is equal to minus rho arrow bar plus Z AZ bar. Mod R bar is equal to square root of rho square plus Z square. Mod R bar whole cube is equal to square root of rho square plus Z square whole cube. Rho square plus Z square 1 by 2 whole cube. Therefore, mod R bar whole cube is equal to rho square plus Z square 3 by 2. Find out DL bar cross R bar. We know that DL bar is equal to rho D phi A phi. DL bar is equal to, we know that DL bar is equal to dl bar is equal to rho d5 a5 bar, and r bar is equal to minus rho a rho bar z dz bar. Find out dl bar cross r bar. A rho a5 az, a rho a5 az. For dl bar, only d5 a5 is there, that is rho d5. The remaining are option 0 0. Here a rho bar means minus rho, a5 is 0, az bar is z. Calculate this one, determined value. A rho, consider a rho, consider a rho bar into rho d5 z minus 0, need not mention. A5 for a5 0 into z 0 minus rho into 0 minus rho into 0 0 plus az 0 into 0 minus into minus plus rho square d5, rho square d5 into az. This is the dl bar cross r bar. But dh is equal to, we know that dh is equal to the magnetic field at a point P is equal to I dl bar cross r bar by 4 pi mod r whole cube, mod r whole cube. We know that dl bar cross r bar is I into, this is the dl bar cross r bar, rho z, rho z, a rho d5, a rho d5 plus az rho square d5, az rho square d5 by 4 pi into rho square plus z square 3 by 2, rho square plus z square whole power 3 by 2. This is the dh. In this case here, this is the coordinate system x, y, and z. This is the point P here, point 1, small current element of length dl, making an angle phi. Here minus this one is rho, minus rho a rho. This one is a rho. dh due to this point, due to rho, minus a rho and a rho are cancelled to each other. Therefore, this term is equal to 0. dh bar consists of two components, ar and a rho and a rho and az. A rho and az. Due to radial symmetry of a rho, this one is a rho and this one is minus a rho. Components are going to cancel to each other. A rho and minus a rho minus a rho, 0. So h exists only, dh bar exists only along the axis in z direction. The dh bar is exists only along the axis, z axis. This one is z axis. Then finally, dH bar is equal to I into rho square d phi Ez bar by 4 pi rho square plus z square 3 by 2. So, why this is 0? I will write here. dH bar consists of two components, aero bar, this one is aero bar, and AZ bar, and AZ bar. Due to radial symmetry, due to radial symmetry, all aero bar components are going to cancel each other. So dH bar exists only along the axis in dz bar direction. Very, very important. Next point is here is d phi. In case of cylindrical coordinate system, we use cylindrical coordinate system. The rho values limits are like that: 0 less than or equal to 5 less than or equal to 2 pi, and minus infinity less than or equal to z less than or equal to infinity. But we know that dH bar is equal to I rho square d phi Az bar by 4 pi rho square plus z square whole power 3 by 2. But H bar is equal to integral of, here d phi is there, we use phi limits. Phi is equal to 0 to 2 pi I rho square Az bar along Az direction only, d phi by 4 pi rho square plus z square whole power 3 by 2. Therefore, H is equal to I rho square Az bar by 4 pi rho square plus z square whole power 3 by 2. D phi is equal to 0 to 2 pi. Therefore, I rho square Az bar by 4 pi rho square plus z square whole power 3 by 2. Integral of d phi is phi in the limits 0 to 2 pi. I rho square Az bar 2 pi minus 0, 2 pi by 4 pi rho square plus z square 3 by 2 ampere per meter. Here pi p is cancelled 2 times. Therefore, H bar is equal to I rho square by 2 into rho square plus z square 3 by 2 Az bar amperes per meter along Az direction only. Suppose the point is shifted at the center of the circular loop, that is z is equal to 0. Here this is the circle. This is the point here on the axis of the circular loop. Suppose this point is shifted to center In previously, the point from the origin, the point P is from the origin is at Z. Okay, here the point P is at origin. That means Z is equal to 0. If if point P is shifted, if point P is shifted at the center of the circular loop, that is Z is equal to 0. Therefore, H is equal to I rho square by 2 into Z is equal to 0 means 2 rho square 3 by 2 AZ bar. That is I by 2 rho cube rho square AZ bar. That is equal to H is equal to I AZ bar by 2 rho. This one is amperes per meter. The point is shifted at the center of the circular loop. That means that is Z is equal to 0. This is the magnetic field intensity at a point P on the axis of the circular loop. That is Z axis. The point P is shifted to Z origin. Next, find out magnetic potential at a point P. Magnetic potential. Magnetic potential is represented by Vm. We know that the magnetic potential formula is Vm is equal to minus A to B H bar dot dl bar. H bar dot dl bar. Already determined H is equal to magnetic field intensity at a point P on the axis of the circular loop is H is equal to I rho square 2 rho square Z square whole power 3 by 2 AZ bar. In case of circular loop, in case of Cartesian coordinate system, dl bar is equal to d rho a rho bar plus rho d phi a phi bar plus dz az bar. Here az is there. Vm is equal to minus a to b. H bar is I rho square 2 rho square plus z square 3 by 2 az bar dot dl is 0 a rho bar rho d phi a phi bar plus dz az bar. Here az bar dot arrow is 0. Az bar dot here a 0 arrow bar rho d phi a phi bar. Az dot a phi is also 0. Finally, Vm is equal to minus a to b I rho square 2 into rho square plus z square 3 by 2 az bar dot dz az bar. Therefore, Vm is equal to minus a to b I rho square 2 into rho square plus z square 3 by 2 dz. In case of cylindrical coordinate system, dz is equal to, in case of cylindrical coordinate system, dz minus infinity, z value is minus infinity less than or equal to z less than or equal to infinity. Therefore, Vm is equal to minus infinity to plus infinity I rho square 2 rho square plus z square 3 by 2 dz. But let z is equal to rho tan theta. Dz is equal to rho secant square theta d theta. Lower limit is minus infinity. Lower limit, that is z is equal to minus infinity. Minus infinity is equal to rho tan theta. Therefore, tan theta is equal to infinity minus infinity. Therefore, theta is equal to minus pi by 2. Upper limit, z is equal to infinity. Infinity is equal to rho tan theta. Therefore, tan theta is equal to infinity. Infinity. Therefore, theta is equal to pi by 2. Theta is equal to pi by 2. Therefore, Vm is equal to minus pi by 2 to plus pi by 2 to I rho square 2 rho cube rho square here. Rho z is rho tan theta. Z square is rho square tan square theta into 3 by 2. But dz is equal to, here dz is also there, rho secant square theta d theta. Rho here rho secant square theta into d theta. This one is rho square. Minus I by 2 minus pi by 2 to plus pi by 2 to rho square into rho cube. This one is rho cube. Secant square theta d theta by here rho square whole power 3 by 2. 1 plus tan rho square is common term. 1 plus tan square theta is secant square theta whole power 3 by 2. Here rho cube, this one, here rho cube. This rho cube, rho square is common term, rho square into whole power 3 by 2, that is rho cube here. This one is rho cube, this is rho cube. This rho cube under this rho cube is cancelled. This one is secant square theta, this one is a secant cube theta. For minus I by 2 minus pi by 2 to plus pi by 2. Secant square theta by secant cube theta, that is 1 by secant theta d theta, that is equal to minus I by 2 minus pi by 2 to pi by 2. 1 by secant theta is cos theta d theta. Integral of cos theta is sin theta. Sin theta pi by 2 to minus pi by 2 minus I by 2 sin pi by 2 minus of sin of minus pi by 2. that is minus I by 2, sin pi by 2 1, sin minus of pi by 2 is minus sin pi by 2, minus into minus plus 1, for 2 is cancelled, therefore minus I, Vm is minus.